Hi, it's time for another math. Easy solution. Turn discuss further into calculus with parametric curves and continue on the tangent series, and now go over part 2 of example 2. And make sure to watch my part 1 of the example 2 in my earlier video. Before I get to the example, I just want to state I have a Patreon account, and first person to donate even just $1 gets a shout out on the next video. So far I have 0 patrons, hashtag sad face. But yeah, if you want to help out, donation would go a long way. Anyways, let's move forward. In this example, I'll go over part B. In my earlier one, I went over part A, so make sure to watch that. And recap on part A, what I did was, what the question stated was, find the tangent to the cycloid, and these are the parametric equations for it. X equals to r times theta minus sine theta, and y is equal to r times 1 minus cos theta. And make sure to watch my earlier videos on the cycloid, which I show the proof of it and more on that. And I'll put all the links in the description below. And this one, I found a tangent of the cycloid to the cycloid at the point where theta equals to pi over 3. But in this part, it states at what points is a tangent horizontal and when is it vertical. So let's look at the first part here. So for B, for horizontal tangents, what we have is when when the tangent is flat. So horizontal tangents is when we have a flat line. In other words, a derivative dy over dx is 0. So it's not increasing or decreasing. It's just a flat line. So again, recall from part A or part 1 that I showed that the derivative for this particular cycloid is equal to dy over dx equal to sine theta over 1 minus cosine theta. So in order for this to equal to 0, what we need is, we need sine theta equals to 0, but we also need and the bottom not to equal to 0. So we can't have 1 minus cosine theta, so this is not equal to 0. So we do not have a scenario where you have a 0 over 0 scenario, which is undefined. So we have to have these cases, and then this one you could simplify this further and move this over here and just move the negative cosine on the other side, make it positive. So we have the scenario where cosine theta is not equal to 1. It's the same thing. Now, so we need to make sure these two conditions are met for it to be equal to 0, for us to have a horizontal tangent. Now, to find these particular conditions, we could just graph the sine and cosine curves and see how their behavior. So if we were to graph, let's say y and theta here, and let's graph cosine first. So cosine looks something like this. I'll draw it like this, and then it just keeps repeating itself, etc. And same way if you go backwards, it just repeats itself like that, and it repeats itself every 2 pi. So like that, and this value here is 1, and it fluctuates from 1 to -1 is across here. So these are all negative ones, and then the top is all 1s like that. And now if we were to draw sine theta, we get something that looks like this, where whenever it's 1, it goes to 0 here, and then when this cosine is 0, we have sine going upwards like that. And then just to make it easier to draw, so then it goes to 0 when this is -1, like that, and then it maxes out here, and it goes to 0 here. And it also has a period of 2 pi. So it basically, from 0 to 2 pi, it just starts repeating itself, and likewise, and even over here. So this maxes out there, and then when this is a max, it goes back down to 0 across like that. And that's basically how the sine function is. So this one is sine theta, and our cosine, I'll write this here. This is cosine theta in black, like that. So now let's look at when the conditions are met. So when sine theta is equal to 0, at this point is 0, but we have cosine theta is equal to 1 here, so we can't have this case. But now when we look at from the period from 0 to 2 pi, we see that, at this point, this sine theta is 0, and here is not equal to -1. So at this point is at pi, like that. Yeah, so we have this case, and then as you can see, because of the nature of trigonometric functions, they're periodic and they just repeat itself. And in these two cases, cosine and sine, they repeat itself every 2 pi. So between 0 and 2 pi, the only cases are, well, at this point here only. When you go to 2 pi, we have sine is 0, but then we have cosine is 1, so doesn't work. So then we go from 0 to 2 pi is only pi, but then this repeats itself every 2 pi. So we can go here, and then you can see the point here. Sine is 0, cosine is -1, and then what we end up having is, well, the difference between these two is just 2 pi. And also, likewise, if you were to graph this all the way across, you'll notice somewhere in between as well at this 1 here, this is also at 2 pi. And you can just extend this, and you'll notice that when this is maximum at the bottom, and then this is at 0, like that. And this is at 4, actually not 4, it's at 3 pi. And then over here, this is at -pi. We just moved over by 2 pi. So in other words, we can just move every 2 pi, but starting at this pi spot or -pi, and then we'll go from, let's say, -pi, there's 3 pi, and then what actually happens is it's an odd number of pi's. So basically, thus, sine theta equals to 0, and, it's always important to keep the and there, and cosine theta is not equal to 1, but what actually happens is, well, cosine theta is equal to -1 in this particular case, equals to -1, like that, which is again not equal to 1, and this is at, well, theta is equal to, we can start off at pi right here, and then we could just add every 2 pi, 2 pi n, where n is just an integer. N is integer like that. In other words, we could have n is equal to 0, 1, 2, 3, or -1, -2, etc. And you could see how this plays around. If you have 0, we just get pi. If we have 1, we get, well, 2 pi plus pi is 3 pi. If we have -1, we just get pi minus 2 pi. That's just -pi. So in other words, this we have, and we can also simplify this further, take the pi out, then we can have 1 plus 2n, and again this equals 2. You could have it as, if this is 0, we just get pi. If it's 1, we get 3 pi, or we can also get, if we have a -1, we get a 1 minus 2, that's a -1, so -pi, etc. If it's -2, we get -4 plus 1, that's -3 pi, etc. But as you see, it's odd numbers, and it keeps going on. So we could even simplify this further and write theta is equal to m pi, like that. And where m is a, so where m is a odd integer. Yeah, so we have odd integer, and we can only, so no even numbers. So we can go with, we can still go with 0. No, actually, no, we can't go with 0. 0, I'll consider that even. If you put 0, we get theta is equal to 0, and we actually, yeah, we can't have that, because then we have cosines 1. So this is going to be 1, -3, 3, -1, etc., 5, 7, 9, etc. Keeps going on and on. So now that's where theta is. Again, remember, theta is the parameter of the cycloid parametric equations, where basically the parameter is the rotation that the circle makes as it forms the cycloid. But we're asked for what points. So now that we have theta, we can solve for the points. So basically, corresponding points. But now that we have the parameters are, yeah, and these corresponding points, well, we know that x is equal to r theta minus sine theta, and y is equal to r 1 minus cosine theta. So what we end up having is x equals to r theta minus sine theta, and we could just plug this theta inside. We get r m pi minus, well, sine of m pi, like that. But then we know that this just goes to 0. So what we're left with is equals to, this is going to be m pi r, where again m is just an odd integer, and then the y value is r 1 minus cosine, cosine theta, which equals to, well, 1 r, and this is going to be 1 minus cosine of this is m pi, and we showed that again, m is odd integer here, and the cosine is always -1. In every single one of these cases is just -1, -1, -1 over there. So this goes to, well, -1. So now we have a 1 minus a -1. That becomes plus 1. So in other words, we get 2r like that. Yeah, so in other words, the corresponding points are, the x-coordinate is m pi r, and the y is 2r like that. So we have here, and for example, we get if, and these are all odd, so we can have if m is 1, we get pi r 2r, and then if m is -1, we get -pi r 2r, and then if it's 3, for example, we get 3 pi r 2r, and basically we can go further and further, 5 pi r 2r, etc. It just keeps going on and on. And now if we were to graph this out, and here I've graphed it using the Desmos graphing calculator, and here's the link to it. If you just click it, it will load it. It's a pretty cool calculator. Let me just open it. Yeah, so here's the calculator, or the graph that I made from my earlier video. You could just hide this. This is from part A, where that's the line tangent to that one there. That's part 1 or part A. So we have this curve here, and I have chosen r as this. And just like always, you can't make theta, I can't put the theta symbol in here, so I just put t instead, and this one's from -6 pi to 6 pi. We get a curve like this, a cycloid curve like that, and basically where r is 1 here. So when we do this, we have, again, r is 1, and what we notice is at this point, this is actually when you have, this is at pi. The distance is pi r, but since r is 1, it's just going to be equals to pi, like that. And likewise here, this is 2 times, yeah, this is 1, 2, this is, or 2r, which equals to 2 in this case, because r is 1. So as you can see here, it's a flat line, so we expected this anyways. So this is at pi r, and then we have a flat line like this. This is, again, derivative dy over dx is equal to 0. This is y, this is x, like that, and this is every 2 pi, and then the arc, each arch like this is actually 2 pi distance, because it's, again, the circle rotates a full distance, which is 2 pi, just the circumference. This is actually 2 pi r, but since r is 1, it's just 2 pi. So, and then we have, this is, if that's at pi r, this point right here is going to be 3 pi r, just separated by 2 pi, and likewise we have another flat line here. This is at -pi r, and likewise over here this is at 5 pi r, etc. So now let's look at the second part of this this part 2, which is looking at the vertical asymptotes, or the vertical tangents. So we can write vertical tangents here. And what we'll notice is, basically from this graph, you could see that the tangents, it appears to be somewhere across here and here. So from this graph it appears, so I'll write that from the graph, it appears that we have, it appears that, yeah, that the vertical tangents are at theta is equal to, well, we have 0 here, and then the distance again is 2 pi r across 2 pi r, but then for theta this is at 0, and then it goes all the way across here. This is 2 pi, 4 pi, etc. So in other words, we have 2 pi n, where again n is a positive integer, or just any integer. N is equal to integer, like that, and this equals 2. Well, you could have it as -1, -2, 0, 1, 2, 3, etc. like that. Yeah, so in other words, this one could equal 2, 0, -2 pi, 2 pi, 4 pi, etc. So that's what it appears to be, but we can actually verify this. So we can write, we can verify this. And to do that, well, we could write limit as, well, theta approaches 2 n pi, or 2 pi n. But then since we're approaching it from, well, different areas, this is going to be from the, let's go from the right side. So we approach it from this side like that, or this side like that. So what we end up having is from the positive side, from the right side, is we might get a different answer. So we have, so then we take the limit of this dy over dx of the derivative to see where it goes, because basically what we want, if it's a vertical asymptote, we want the bottom. So we want a scenario where we have a 1 over infinity. Actually, not a 1 over infinity, we have a 1 over 0 that approaches infinity. That's the only way you get a vertical asymptote like that. So that's what we want, and we can, well, plug that in. So we have limit as this equals to 2 pi n from the right side, and this is going to be, just plug this in, the derivative is sine theta over 1 minus cosine theta. But since this is 2 pi number, you're going to have a 1 value. So this is approaching a 1 minus 1, and at the top is 0. Then we just have a 0 over 0. So this is indeterminate. And again, you could see it over, let's say, over this curve. Whenever you have theta is equal to 0, we get it over here. So we have a 0, and then the cosine is 1. 1 minus 1 is, well, 0. And then likewise over here, 2 pi with the same thing, like that. So the problem is we can't do this directly, but we can, well, recall L'Hopital's rule, and I'll put that in the link below. That's the proof for it. So L'Hopital's rule, whenever we have a indeterminate limit like this, a 0 over 0 or infinity over infinity, what we could do is take the derivative, and you can see the proof for this in a video link below. So what we can do is, well, take the derivative. So this limit theta 2 pi n plus of the sine theta over 1 minus cosine theta. This equals to, well, the derivative now. Limit as theta, this is approaches 2 pi n plus, so d over d theta of sine theta over d theta of 1 minus cosine theta. So when we take the derivatives, what we end up getting is something that looks like this. The derivative of sine, that's just cosine theta. So we get limit as theta approaches to 2 pi n. This is just tedious stuff. From the right side, we get this is derivative of sine theta, just cosine theta over now we have derivative of 1 minus cosine theta. 1 goes to 0, negative cosine theta, derivative is just negative sine theta, but there's a negative already, so it becomes positive sine theta, like that. And now what we have is, well, this one here, the cosine theta approaches 1, and this one right here approaches, well, 0. So we get a scenario of 1 over 0, but this is from the positive side. So in other words, yeah, so we have it approaching a 1 over 0 from the right side, like that, because you can see over here, because we're approaching theta from the right side, it's from this positive side. We have sine is positive when it's approaching 2 pi when n is equal to 1. We have it over here, and this is positive, so we're approaching from the right. If it was from the left, we'll have a negative, like that. So what we end up having is it's approaching from the right side, and then we get a 1 over 0, which is, well, infinity, or positive infinity, like that. And also similarly, what we get is if we were going from the left side, similarly, limit as theta approaches to 2n pi from the left side of put the negative sign, meaning the left sides of sine theta over 1 minus cosine theta. Again, we're going to have the exact same thing where we have the 0 over 0, do the L'Hopital's rule, and then this ends up being, well, we could just erase this and do the derivative, just start off from here, which is actually over here, cosine theta over sine theta, so we get cosine theta sine theta. And then what we end up having is is this one here's, again, this is approaching 1, this is approaching negative 0 from the left side, so it's going to be like negative or approaching negative 0, like that, or negative 0.000, etc. So it's on the negative side, so what we end up having is a 1 over negative 0 scenario, which is, well, negative infinity. So 1 divided by 0 is infinity, but now we have a negative infinity. In other words, we still have an asymptote line. In other words, the tangent here on the left side is going to be like this going down, and it's still a vertical tangent, and on the right side is positive infinity. Positive infinity, negative infinity, like that, but it's still a vertical tangent. Thus, indeed, we have vertical tangents, and these are at, so at theta is equal to 2 pi n, or in other words, x is equal to, well, you could just plug this in, x is equal to r, and now we have theta is 2 pi n plus sine 2 pi n, like that, where again sine goes to 0, so this just equals to 2 pi n r. That's the x coordinate. And then for y is, again, y is just r 1 minus cosine. Yeah, 1 minus cosine, also this is a minus, but still 0, doesn't change anything. This is 1 minus cosine 2 pi n, which again, all of these ones were going to 1. So this is approaching 1, 1 minus 1 is just 0. So those are just the 0 points, like that. In other words, we have it at 2 pi n r 0, where n is just an integer, like that. N equals to integer. And so indeed we have it there, and you could even see it all across here. 0, then we have over here 2 pi r, and then all the way across this point here is at 2 pi, this is going to be 2 pi, n is 2 r, so in other words 4 pi r. And all these points are 0 across. So anyways, that's all for today. If you learned from this pretty extensive example, part 2. I should have broken it up into 3 parts. I didn't know the last part was going to take that long, but anyways, hopefully you follow along. You could also watch it in separate videos if it takes long, and you can also speed it up if it's too long. And also, yeah, donate if you like these videos. Anyways, thanks for watching. Like always, you can download these exact notes in the link below. Thanks for watching, and stay tuned for another Math Easy solution.